Welcome to the deep dive. Okay, let's just jump right in. If you have ever had to design an application for the cloud, you know that the AWS compute section, it's not just a few choices, it's this sprawling, confusing landscape. It feels less like picking dinner and more like deciding what engine, what fuel, what transmission you need just to get a car running.
It is overwhelming, I agree. But this is, the absolute core of cloud architecture. Choosing the right compute solution, that's like selecting the engine room for your application. So today our focus is really on designing elastic, high-performing compute solutions. Stuff that can handle, well, anything from a trickle of traffic to a huge surge without breaking.
Exactly. And our mission here is to give you that shortcut to architectural mastery. We want to stop talking about basic definitions.
Mm.
We want to start talking about strategic decisions.
hmm
We're going to map out the compute spectrum. We're going to talk about smarter scaling, and then get into why decoupling is so critical for resilience.
It's all about building systems that aren't just fast. They have to be efficient and resilient. And to start, you have to choose your compute model. And that fundamentally just boils down to one question. How much control do you want versus how much agility you need?
Okay, so let's define those two ends of the spectrum then.
Yeah.
On one side, we have maximum control, the raw power of having complete oversight.
That's Amazon EC2, the Elastic Compute Cloud. Think of it like renting a massive empty warehouse. You get the keys, you pick the size, and then you install everything yourself. The flooring, the security, the shelves.
So you have total control.
Total control over the operating system, the patching, every little detail. But you also shoulder all of the responsibility for its upkeep.
And we swing all the way to the opposite end,
Yeah.
where the focus is just, pure agility, zero management.
That's the serverless end. And that's dominated by AWS Lambda. So if EC2 is the rental car where you're doing the oil changes, Lambda is the Uber. You just press a button, your code executes, and you only pay for the duration of that trip. AWS manages everything else, the hardware, the scaling, all of it.
That initial decision feels so crucial. Full management responsibility or just run my code.
Yeah.
But modern apps, they're rarely one big server or one tiny function, right? They're usually these complex networks of microservices.
And that brings us right into the middle ground, which is containers. When you need consistency, rapid deployment, portability, containers are the answer. We're talking about orchestration here, mainly Amazon ECS or EKS, which is managed Kubernetes.
Right. But when I first heard about containers on AWS, my first thought was, great, now I have to manage the EC2 instances that run the containers, which that just sounds like more work.
And that's the exact insight that led to what I'd call the high-performance pro tip here, which is AWS Fargate. Fargate is essentially the serverless way to run your containers in both ECS and EKS. This is so critical because it eliminates all of that undifferentiated heavy lifting. You just define the container and Fargate runs it. You don't have to provision or patch or scale the underlying cluster.
Okay, so Fargate gives us the portability of containers
Yeah.
and the agility of serverless. You're basically getting rid of the need to manage infrastructure capacity.
Precisely. It lets the team spend, 100% of their time on application logic, not on OS optimization or patching. When you think high performance, minimizing operational friction is step one.
That seems like a clear winner for keeping development moving. But okay, regardless of which model we pick, EC2, Lambda, Fargate, the next big challenge is elasticity. We all know auto-scaling is key, but why do so many people still get it wrong?
They get stuck on the most basic metric. The common misconception is that auto-scaling just means checking average CPU usage. If the CPU hits 80%, spin up another server.
Which, on the surface, that seems logical. Servers working hard, it must need help.
It is logical, but it's often too late. Or it's just misleading. Imagine your web server is configured to instantly reject requests if it's overloaded. Your CPU might look perfectly healthy, maybe idling at 40%. But if you're rejecting thousands of users, they're all waiting, and your application is delivering a terrible experience. The CPU doesn't reflect the demand.
So the high-performing strategy ignores utilization and focuses on the actual work waiting to be done.
Absolutely. You need the right demand signal. You have to scale based on leading indicators of demand, not lagging indicators of resource exhaustion.
Okay, so let's get specific. What are those metrics that you should be implementing right away?
For a typical web app behind a load balancer, checking CPU is almost always the wrong move. The better metric is request count per target. This tells you exactly how many inbound requests are hitting each server. If you set a target of, say, 1,000 requests per minute per server, auto-scaling will add resources before your servers get overloaded.
That makes perfect sense. I mean, traffic is the purest form of demand.
Exactly. Now let's think about the back end. Let's say you're running a service that processes, I don't know, complex financial reports. Those reports are going to queue up. The critical metric here should be the backlog per instance. This ensures you scale based on the size of the queue of unfinished work.
So if I have 10,000 reports waiting, and each of my workers can process 1,000 per hour, I should have 10 workers running, not based on how hard their CPUs are spinning, but on the demand that's literally waiting in line.
Precisely. And if that queue grows to 50,000 reports, the backlog metric spikes, and auto-scaling immediately spins up 40 more workers to drain that queue. It's scaling based on demand signals. That's true elasticity. It's a huge shift from just watching CPU gauges.
That level of responsiveness is vital. But scaling is only half the battle. We talked about designing systems that don't just collapse when one part fails. How do we ensure that integrity?
This is where we have to talk about decoupling. It is non-negotiable. You have to design your architecture to prevent that house of cards effect. In a tightly coupled system, if service A talks directly to service B and B crashes,
Service A crashes too, and the whole thing freezes.
the whole system. So we need to move to a loosely coupled system, and the key tools for that are Amazon SQS, the simple queue service, and Amazon SNS, the simple notification service.
They sound similar. How do they divide the labor?
SQS is your queuing mechanism. Think of it as a secure, durable safe box. It's a buffer. An upstream service leaves a message, a transaction maybe, in the queue. The downstream service pulls it out when it's ready. If that receiving service is slow or overwhelmed, the queue just fills up. And that not only preserves the data, but it gives us that perfect signal, the growing backlog metric for auto-scaling.
Right, so SQS is for deferred tasks where processing must be guaranteed, but not necessarily immediate.
Exactly. SNS, on the other hand, is the megaphone. It's for messaging and the pub/sub pattern. You publish an event once, and it broadcasts to many subscribers at the same time. For example, an event like new user signed up happens. SNS can broadcast that message to, say, 5 different downstream services analytics, the welcome email service, the security logs, and so on.
Okay, so if guaranteed delivery to a single worker is the goal, you use SQS. If broadcasting one event to many listeners is the goal, you use SNS.
That's the core difference. SNS is immediate fan-out. SQS is durable buffering. And the resilience benefit is just huge. If our order service crashes, the payment service doesn't even know it happened. SQS is just patiently holding those messages. The system waits instead of crashing.
That protection against cascading failures is, well, it's what separates a resilient app from a fragile one. Okay, let's talk about the exceptions. We focused on agility, but what happens when a task just needs massive resources or runs way longer than Lambda's 15-minute timeout?
That's when we call in the specialized heavy lifters. We have to recognize the limits of the general purpose tools.
And what's the tool for those really big, long-running batch jobs that might take hours or even days?
That is AWS Batch. If EC2 is the rental car and Lambda is the Uber, AWS Batch is the construction company foreman. You hand it a list of complex jobs like rendering 10,000 3D models, and Batch automatically provisions all the compute, runs the jobs, manages dependencies, and then scales everything back down to 0 when it's done.
So it just handles the provisioning headache for those big scheduled tasks. And what about when it's not duration, but just sheer data volume, petabytes of information?
That's Amazon EMR, Elastic MapReduce. EMR is the big data powerhouse. If your scenario involves frameworks like Hadoop or Spark, or processing enormous volumes of logs, EMR is the specialized tool that handles that complexity. It's built to run those massive data processing jobs.
Excellent. Okay, let's turn to the final frontier of performance, the network edge. We've established latency as the enemy, especially for global apps.
Absolutely. Every single millisecond counts for the user. Edge computing is the architecture that pushes compute closer to the user to minimize that physical distance and therefore minimize latency. Instead of a round trip to a central data center maybe thousands of miles away, the logic runs right where the user is.
That sounds like a big challenge. How does AWS let us run code right on the edge?
Through services like Lambda at Edge or CloudFront functions. When a user requests content through CloudFront, which is the AWS CDN, you can run a small, fast piece of Lambda code at the closest edge location. This code can handle things like authentication checks, URL rewrites, or even personalization before the request ever travels back to your central region.
So you're cutting latency from hundreds of milliseconds down to maybe 10 or 20. Just by avoiding that cross-continent trip, the user experience feels instantaneous.
Exactly. It's a key strategy for any global low-latency application.
Before we wrap, I want to circle back to Lambda optimization, because this insight, it just defies traditional logic. We talked about finding the Goldilocks zone.
This is where architects really earn their pay. When you configure a Lambda function, you allocate memory. The standard, sort of simplistic approach is to just allocate the bare minimum you need to avoid errors.
Right. But the critical nuance is that when you increase the memory, AWS proportionally increases the CPU power too,
Mm.
and the network bandwidth. You're effectively paying for memory, but you're buying performance.
That's the beautiful paradox of it. If a function is CPU bound, meaning it spends most of its time calculating giving it more memory, say, bumping it from 128 millib to 512 millib often results in the task finishing in half the time, or even less.
Wait, if I increase the memory, the function runs faster. And since Lambda bills by the millisecond, I'm charged a higher rate but for fewer total seconds. Does that math actually make it cheaper?
It often does. You might pay twice the rate per second for the higher memory config, but if the function finishes in less than half the time, the total cost for that execution is lower. The optimal decision isn't about picking the smallest size. It's about finding that balance where performance meets cost efficiency, the true Goldilocks zone.
That is a powerful final takeaway.
Wow.
We covered a huge amount of ground, from the controlling EC2 to the agility of Fargate and Lambda at Edge. We established that true elasticity uses demand metrics like backlog per instance, not just, watching CPU. And most importantly, resilience is built on decoupling with SQS for buffering and SNS for fanout.
Right. And remember that subtle optimization trick. More memory can actually lower the cost of a CPU-heavy Lambda function. We've discussed the efficiency gains there in that Goldilocks zone, which raises a final provocative thought for you. If you manage a complex system with hundreds of functions, how much time should an architect realistically spend optimizing the sizing for every single one? When does that pursuit of the ultimate 1% saving become, a greater and less efficient drain on the team's time than just accepting a slightly higher but simpler configuration? That's the real-world trade-off between perfection and practicality in the cloud.